Trigonometric functions are used to model recurring phenomena such as oscillations and vibrations. To visualize how trig functions can model vibratory motion, imagine the ball to the right is attached to a spring hung from the ceiling. If the ball is pulled down a distance of a and then released, and we neglect the effects of friction and air resistance, then the ball will continue to oscillate up and down. These oscillations are called simple harmonic motion. Let's look at the definition. An object moving along a coordinate axis such that the distance d from the origin at time t is given by either d equals a times the cosine of omega t or d equals a times the sine of omega t is said to be in simple harmonic motion. The motion has an amplitude equal to the absolute value of a, which is the maximum displacement from the center line or equilibrium position. That center line is also called the rest position. The period of the motion is equal to 2 pi over omega, where omega is positive. The period is the time required to complete one cycle from the equilibrium position back to the equilibrium position. Let's look at an example. A ball on a spring is pulled down 5 inches below its rest position and then released. Because it's pulled below its rest position, we're going to say that a is equal to -5. That's what we're going to use for the value of a, and it's negative because the ball starts below its equilibrium position. The ball takes 3 seconds to complete one cycle. What is the equation of the ball's simple harmonic motion? Well, we already know the value of a, and because it starts at its negative amplitude, -5, we're going to use the cosine instead of the sine. If the ball had started from its rest position, we would have used the sine instead of the cosine. So here's what we're going to do. If we let the time that the ball is released be t equals 0 seconds, then the maximum displacement of the ball is equal to 5 inches because we have that a is equal to -5, and we know that the maximum displacement is the absolute value of a. We also have that the period is equal to 3 seconds because it said it takes the ball 3 seconds to complete one cycle, and we know that the period is the time it takes to complete one cycle. We have a is -5. We have that the period is equal to 3, but we also know that the period is equal to 2 pi over omega, so we have that 3 is equal to 2 pi over omega. Solving that equation for omega, we get that omega is equal to 2 pi over 3, and now we have the model. We're using this cosine model, so we have that d is equal to a, which is -5, times the cosine of omega, which is 2 pi over 3 times t. So this is the equation of the ball's simple harmonic motion. Let's go ahead and define what the frequency is of the harmonic motion. Simple harmonic motion frequency. Given an object in simple harmonic motion with a model d equals a times the cosine of omega t, or d equals a times the sine of omega t, the frequency f of the object is defined as f is equal to omega divided by 2 pi, where omega is positive. If you recall, we just defined the period to be 2 pi over omega, so the period and the frequency are reciprocals of each other. Let me give you an example. This first ball here to the left takes 2 seconds to complete one full cycle. So the period of that ball is 2 seconds. On the other hand, the frequency is the amount of cycles that the ball will complete in a second. And since it takes 2 seconds to complete one full cycle, in 1 second it's only done half of a cycle. So the frequency would be half of a hertz. On the other hand, this ball completes one full cycle in a half a second. So because it completes one full cycle in a half a second, the frequency, it actually does 2 full cycles per second. So the frequency is 2 hertz, 2 cycles per second. Let's take a look at an example. An object moves in simple harmonic motion modeled by the equation d equals 9 times the cosine of 4 pi over 3t, where t is measured in seconds and d in inches. Find the maximum displacement, the frequency, and the time required for one cycle. Well, given this formula here, we can find the frequency, but previously we defined the maximum displacement to be the amplitude of the function, and the amplitude of this function is 9. So we have 9 being the maximum displacement. We also know that the time it takes to complete one full cycle, or the period, is equal to 2 pi over omega, where omega in this case is 4 pi over 3. So if we want to find the period, we take omega, which is 4 pi over 3, and we remember that the period is equal to 2 pi over omega, which would be 2 pi over 4 pi over 3. Simplifying this, I see that the pi's cancel out, and I'll be dividing 2 by 4/3. If I flip the 4/3 over and multiply, I will get 6 over 4, which reduces to 3 over 2. 3 over 2 is exactly 1.5 seconds. So this model here, the ball on the spring or whatever is vibrating here, takes 1.5 seconds to complete one full cycle. And we know that the frequency is the reciprocal of the period, so the frequency is just going to be the reciprocal of 3 over 2, 2 over 3. Let's use the formula. It says the frequency is equal to omega over 2 pi, and omega is 4 pi over 3. So the frequency is then 4 pi over 3 over 2 pi, and you flip this over, the pi's cancel, you get 4 over 6, and 4 over 6 reduces to 2/3. So the frequency is 0.67 hertz, and that is how we find the frequency, the maximum displacement, and the amount of time required to complete one cycle.